Right now, as you listen to these words, something extraordinary is happening all around you. Every breath you take, every heartbeat, every flicker of light from your screen is part of an invisible, cosmic process that governs everything from the birth of stars to the formation of your thoughts. Scientists call it entropy, and it might be among the most profound principles in the universe that you've never truly understood. This video is for educational purposes and examines published scientific research and educational materials to explore one of nature's most fundamental principles. Interpretations are attributed to their scientific sources and may evolve with new evidence. Imagine for a moment that you could see this force at work. You would witness coffee cooling in your cup, ice melting in summer heat, and galaxies slowly burning out their nuclear fuel. You would see time itself flowing in one direction, never backward. You would observe life emerging from chaos, only to eventually return to it. This is entropy in action, and it's been shaping reality since the very beginning of time. The story begins in the 1800s with a German physicist named Rudolf Clausius, who was trying to understand why steam engines could never be perfectly efficient. He discovered something that would revolutionize our understanding of reality itself. In 1865, Clausius introduced a new concept to science, deriving the term from a Greek word meaning transformation. He called it entropy. But what exactly is this mysterious quantity that Clausius identified? At its most fundamental level, entropy measures the number of possible arrangements that atoms and molecules can take within a system. Austrian physicist Ludwig Boltzmann expanded this understanding, revealing that entropy is essentially nature's way of counting possibilities. The more ways particles can be arranged, the higher the entropy. Consider a simple example that demonstrates this principle beautifully. When you drop a sugar cube into hot coffee, the organized crystal structure dissolves into billions of individual molecules, spreading randomly throughout the liquid. The sugar doesn't spontaneously reassemble itself because there are vastly more ways for those molecules to be scattered than to be perfectly organized. This isn't just a curious observation about coffee and sugar. It's a window into one of the universe's most fundamental rules. The second law of thermodynamics, which emerged from the work of multiple scientific pioneers, including Clausius, Lord Kelvin, and Sadi Carnot, states that entropy in an isolated system can never decrease over time. This means that natural processes always evolve towards states of maximum disorder. Yet this seemingly simple statement carries implications that extend far beyond physics laboratories and engineering textbooks. Einstein himself often emphasized throughout his life that thermodynamics represented one of the most universal physical theories. The phenomenological laws of thermodynamics, he believed, possessed significance that reached far beyond their mathematical expressions, touching on fundamental philosophical questions about the nature of reality itself. Historians note this as an emphasis rather than a formal theorem. Here's where entropy reveals perhaps its most mysterious property. Unlike almost every other quantity in physics, entropy seems to care about the direction of time. Physical laws generally work the same, whether time moves forward or backward, but entropy creates what scientists call an arrow of time that always points in one direction. This temporal asymmetry manifests everywhere around us. Ice cubes melt in hot coffee rather than spontaneously forming from the liquid. A block sliding across a rough surface slows down rather than speeds up. We remember the past but cannot remember the future. These everyday phenomena all stem from the same underlying principle that entropy tends to increase with time. The connection between entropy and memory proves particularly fascinating to researchers. Our ability to form memories has been argued to be fundamentally linked to the second law of thermodynamics. Memory formation requires creating correlations between brain cells and the external world, a process that inevitably increases entropy in our surroundings. This suggestion is an active research area and suggests that consciousness itself might be intimately connected to entropy's forward march through time. But why does time have this preferred direction at all? Some researchers propose that the answer lies in the very beginning of the universe itself. The cosmos appears to have started in an exceptionally low entropy state during the Big Bang, creating a statistical asymmetry that drives systems toward higher entropy throughout cosmic history. Physicist Sean Carroll compares this temporal asymmetry to spatial asymmetry, noting that while physical laws generally remain symmetric when we flip the direction of time, our proximity to the Big Bang creates an obvious distinction between forward and backward in time. Under this interpretation, all arrows of time emerge from our relative position in cosmic history and the special circumstances that existed during the universe's earliest moments. This is a leading explanation, but not the only one. This brings us to one of the most remarkable aspects of entropy's influence on reality. The arrow of time defined by increasing entropy appears to be fundamentally connected to the cosmological arrow of time defined by the universe's expansion. Recent research in entropic cosmology explores the possibility that these connections run even deeper than previously imagined. During the universe's evolution, matter fields inside the cosmic horizon show outward flux during accelerating expansion phases, potentially decreasing local entropy in ways that would seem to violate the second law unless we incorporate the cosmic horizon itself into our entropy calculations. Some models propose that this relationship between cosmic expansion and entropy increase reveals that local apparent violations of the second law might be balanced by entropy changes on cosmological scales. This remains under investigation. The implications prove truly staggering. Modern cosmology recognizes that the universe's initial low-entropy state is widely considered the ultimate source of all temporal asymmetry we observe today. From the simple mixing of cream in coffee to the formation of memories in our brains, every time-directional process can be traced back to this primordial cosmic condition under standard cosmological assumptions, lambda CDM. Consider what this means for our understanding of reality. The universe began in a state of incredible order and has been gradually becoming more disordered ever since. Yet within this cosmic trend toward chaos, pockets of extraordinary organization have emerged. Stars form from collapsing gas clouds, planets coalesce from stellar debris, and life arises from molecular soup. How can increasing entropy lead to such remarkable organization? The answer reveals one of nature's most elegant paradoxes. Living organisms represent what scientists call dissipative structures, systems that build and maintain order by consuming energy and creating more disorder in their environment. Far from violating the second law of thermodynamics, life actually depends on it for its existence. Russian-Belgian physical chemist Ilya Prigogine, who received the Nobel Prize in Chemistry in 1977 for his pioneering work on dissipative structures, demonstrated how thermodynamic systems, far from equilibrium, can behave in drastically different ways from systems close to equilibrium. These structures include oscillating chemical reactions, spatio-temporal patterns, and remarkably, biological organisms themselves. When we examine biological processes closely, we discover that organisms are essentially machines built by evolution to efficiently consume free energy while maintaining homeostasis and engaging in reproduction. Photosynthesis, the primary pathway through which energy enters biological systems, involves energy being degraded and discarded as heat, with entropy increasing substantially more than the order created by the biochemical processes it drives. This principle extends throughout the living world. Every time you move a muscle, think a thought, or digest food, you're participating in entropy's grand dance. Your body maintains its complex organization by constantly consuming energy from food and releasing heat and waste products into the environment. The order within your cells exists only because it creates greater disorder in your surroundings. But dissipative structures possess another remarkable property that Prigogine discovered. When these structures are perturbed or damaged, they can re-establish themselves, implying a form of self-healing. The irreversible processes that create dissipative structures operate within the structures themselves, giving them the ability to restore and heal damage. This characteristic proves fundamental to understanding how biological organisms maintain themselves over time. Recent research has revealed that some dissipative structures exhibit organism-like behavior, reinforcing expectations that studying these systems will provide crucial insights into the origin of life itself. These structures demonstrate nature's ability to create order through disorder, showing how increased entropy production can lead to more complex, self-maintaining organizational patterns. These interpretations remain theoretical and under active investigation. What emerges from this research is a profound realization about life's place in the cosmic order. Rather than being an anomaly that temporarily reverses entropy's increase, life represents entropy's most sophisticated expression. Organisms don't fight against the second law of thermodynamics. They embody it in ways that create unprecedented levels of organization and complexity. This understanding transforms our perspective on biological evolution itself. Evolution becomes not just a process of genetic change over time, but a mechanism through which dissipative structures become increasingly efficient at consuming free energy and creating entropy. The complexity of life emerges from entropy's drive toward maximum disorder, channeled through the constraints of chemistry and physics into forms of organization that would be impossible in equilibrium systems. As we continue exploring entropy's influence on reality, we'll discover how this same principle that drives life's emergence also governs the formation of complex systems throughout the universe, from the self-organization of galaxies to the emergence of consciousness itself. The following chapters discuss these topics in an educational, non-speculative context. But here's where the story takes an unexpected turn that challenges everything we think we know about disorder. Within the mathematical framework of chaos theory lies a remarkable discovery that some researchers describe as one of nature's most beautiful contradictions. Complex systems, from weather patterns to ecosystems, demonstrate that apparent randomness often conceals underlying patterns of extraordinary sophistication. Chaos theory reveals that, within seemingly random systems, exist hidden structures characterized by interconnection, constant feedback loops, repetition, self-similarity, and most remarkably, self-organization. This phenomenon occurs when overall order emerges spontaneously from local interactions between parts of an initially disordered system, triggered by what scientists observe as random fluctuations that become amplified through positive feedback mechanisms. The cybernetician Heinz von Foerster formulated what he called the principle of order from noise in 1960, noting that self-organization becomes facilitated by random perturbations that allow systems to explore various states. This increases the probability that the system will arrive at what mathematicians term the basin of a strong attractor. Building on this work, biophysicist Henri Atlan developed the principle of complexity from noise, while Ilya Prigogine described a similar concept as order through fluctuations. Consider the Belousov-Zhabotinsky reaction, a chemical system that creates stunning spiral patterns and oscillating colors when specific compounds interact under controlled conditions. When spatial effects are incorporated through reaction-diffusion equations, long-range correlations and spatially ordered patterns arise spontaneously. These systems represent dynamic states of matter that emerge as direct results of irreversible processes, demonstrating how entropy-driven chaos can generate breathtakingly organized structures. What makes these discoveries particularly fascinating to researchers is how these patterns exhibit organism-like behavior. When damaged or perturbed, they possess self-healing properties because the irreversible processes that created them operate within the structures themselves. This characteristic mirrors the fundamental properties of biological organisms, suggesting that studying dissipative structures might provide crucial insights into life's origins and organizational principles. While experimental demonstrations exist, broader biological implications remain a topic of ongoing research. The connection between entropy and organization deepens when we explore how information itself relates to disorder. In 1948, Claude Shannon introduced a revolutionary concept in his mathematical theory of communication, defining information entropy as a measure of uncertainty or surprise in transmitted messages. Remarkably, Shannon's formula proved formally analogous, though not identical in meaning, to the thermodynamic entropy equations developed by physicists decades earlier. This parallel between information theory and thermodynamics reveals profound connections between knowledge, energy, and disorder. The principle of maximum entropy states that when we possess incomplete information about a system, we should choose the probability distribution with maximum entropy subject to available constraints. This principle suggests we should select the most unbiased, least structured probability distribution consistent with our current knowledge. Maxwell's demon, a thought experiment proposed by James Clerk Maxwell, illustrates these connections beautifully. The demon could hypothetically reduce a system's thermodynamic entropy by using information about individual molecules to sort them by energy levels. However, as physicist Rolf Landauer and his colleagues demonstrated, to function effectively, the demon must increase thermodynamic entropy elsewhere in the process by at least the amount of information it acquires and stores. Landauer's principle establishes a theoretical lower bound on the amount of heat any computer must generate when erasing information. This connection reveals that knowledge itself carries energetic costs, and that information processing becomes fundamentally linked to entropy increase. Every calculation, every stored memory, every transmitted message contributes to the universe's overall entropy production. Modern quantum computing research continues exploring these relationships, investigating how quantum systems might process information while minimizing entropy generation. Some researchers propose that understanding these quantum information processes could lead to more efficient computing systems that work more harmoniously with thermodynamic principles. These ideas remain speculative, but form an active research field in quantum information science. As our understanding of entropy's role in complex systems expands, researchers have begun applying these principles to phenomena ranging from biological networks to social systems. Within the emerging field of fractal physiology, scientists characterize bodily signals such as heart rate variability and brain activity using entropy measurements and fractal indices to assess system health and diagnose potential disorders. Complex systems theory represents an interdisciplinary domain, drawing contributions from statistical physics, information theory, nonlinear dynamics, anthropology, computer science, meteorology, sociology, economics, psychology, and biology. These systems exist in a domain between deterministic order and complete randomness, occupying what some researchers call the edge of chaos. At this edge, systems demonstrate emergent properties that cannot be predicted from understanding individual components alone. As Nobel laureate Philip Anderson observed, more becomes different when dealing with complex systems. The interactions between numerous parts create coherent behaviors that transcend the properties of individual elements. Network theory reveals how these complex systems organize themselves through what scientists term preferential attachment and scale-free distributions. Social networks, neural networks, and even the structure of the internet exhibit similar organizational patterns despite their vastly different scales and purposes. These networks demonstrate remarkable resilience to random failures while remaining vulnerable to targeted attacks on their most connected nodes. The study of these complex networks has revealed statistical and mathematical principles that appear to govern organization across multiple scales of reality. From the neural networks in our brains to the social networks that connect human societies, similar mathematical relationships describe how information flows, how connections form, and how order emerges from apparent chaos. Research in this field continues uncovering connections between entropy production and network efficiency. Some studies suggest that the most robust and adaptable networks operate near critical points where they maximize information processing while maintaining structural stability. This balance appears to optimize the network's ability to respond to environmental changes while preserving essential organizational features. These conclusions remain models and do not imply deterministic predictions about real-world societies or systems. Recent research has extended entropy concepts into economic systems, proposing analogies where financial value generation parallels entropy production in thermodynamic systems. These economic models suggest that irreversible economic processes, such as market transactions and resource consumption, generate economic entropy in ways that mirror thermodynamic irreversibility. These models are metaphorical analogies, not physical equivalences. Modern organizations increasingly become understood as open, complex, adaptive systems, with fundamental nonlinear structures, subject to internal and external forces that may contribute to chaotic dynamics. Team building and group development are being researched as inherently unpredictable systems where small changes in initial conditions can produce dramatically different outcomes. Career counseling models that incorporate chaotic interpretation of relationships between employees and job markets have shown promise for helping individuals navigate uncertain professional landscapes. By recognizing the complex non-linear nature of career development, counselors can provide more realistic guidance that acknowledges both opportunities and limitations within dynamic economic systems. These applications demonstrate how entropy principles extend beyond physical sciences into human social structures. Economic systems, like thermodynamic systems, tend toward equilibrium states that may not represent optimal outcomes for all participants. Understanding these dynamics helps policymakers and business leaders develop strategies that account for system-level behaviors rather than focusing solely on individual components. The parallels between economic and thermodynamic systems suggest that sustainable economic development might require approaches that work with entropy principles rather than against them. This could involve designing economic structures that channel competitive forces toward outcomes that benefit both individual participants and system-wide stability. These interpretations are illustrative frameworks used by researchers in econophysics and complexity economics. Within medical research, entropy measurements are providing new insights into health and disease. Fractal analysis of physiological signals reveals that healthy biological systems often exhibit specific types of complexity characterized by particular entropy signatures. Deviations from these patterns can indicate developing pathological conditions before traditional diagnostic methods detect them. Heart rate variability analysis uses entropy measures to assess cardiovascular health and autonomic nervous system function. Researchers have discovered that optimal heart rate patterns exhibit neither rigid regularity nor complete randomness, but rather a complex variability that maximizes the system's ability to respond to changing demands. Similarly, brain activity measurements using electroencephalography and functional magnetic resonance imaging reveal entropy patterns associated with different states of consciousness. Some studies suggest that creative problem solving and learning involve temporary increases in neural entropy that allow the brain to explore new organizational patterns before settling into more stable configurations. These findings describe correlations, not causal proofs. Sleep research has identified specific entropy signatures associated with different sleep stages. During REM sleep, brain activity shows increased entropy compared to deeper sleep stages, possibly reflecting the brain's processing of information and formation of new neural connections. Understanding these patterns helps researchers develop better treatments for sleep disorders and cognitive enhancement strategies. Aging research increasingly focuses on entropy accumulation in biological systems over time. Some theories propose that aging results from gradual increases in cellular disorder that eventually overwhelm repair mechanisms. This perspective suggests that interventions designed to reduce entropy accumulation or enhance repair processes might slow aging and extend healthy lifespan. This is a theoretical framework and not a proven medical intervention. These medical applications demonstrate how entropy concepts provide practical tools for understanding and improving human health. By recognizing the role of disorder and organization in biological systems, medical researchers can develop more effective diagnostic techniques and therapeutic interventions. As we approach the culmination of our exploration into entropy's influence on reality, we begin to see how this fundamental principle weaves through every aspect of existence, from the quantum realm to the cosmic scale, creating the intricate tapestry of order and disorder that makes life, consciousness, and the universe itself possible. All scientific interpretations presented here are attributed to their respective research communities and are discussed for educational purposes. But perhaps the most extraordinary revelation awaits us at the very foundation of reality itself, where entropy encounters the strange world of quantum mechanics. Here, in the realm of the impossibly small, researchers have discovered that the classical rules of disorder take on entirely new meanings that challenge our most fundamental assumptions about information, measurement, and the nature of existence itself. Quantum systems exist in what physicists call superposition, where particles can simultaneously occupy multiple states until the moment of measurement collapses them into a single configuration. This quantum behavior introduces a fascinating complication to our understanding of entropy. Before measurement, a quantum system possesses what researchers term quantum entropy, which differs fundamentally from the classical entropy we've been exploring throughout our journey. When scientists measure a quantum system, they irreversibly increase the entropy of the surrounding environment. This process, known as quantum decoherence, represents one of the most profound connections between information theory and thermodynamics ever discovered. Each measurement extracts information from the quantum realm while paying an entropic cost in the classical world. Some researchers propose that this quantum to classical transition might explain why our macroscopic universe exhibits the clear, directional flow of time we experience daily. The constant collapse of quantum superpositions through environmental interaction creates what some theorists describe as a quantum arrow of time that emerges from the microscopic realm to influence macroscopic phenomena. This remains a hypothesis under active debate within quantum thermodynamics. Recent studies in quantum thermodynamics have revealed that even the most fundamental quantum processes obey modified versions of thermodynamic laws. Quantum heat engines, quantum refrigerators, and quantum batteries all demonstrate that entropy principles extend seamlessly into the quantum domain while exhibiting entirely new possibilities for energy manipulation and information processing. These discoveries have profound implications for our understanding of consciousness itself. Some neuroscientists and quantum physicists collaborate on theories suggesting that quantum processes in neural microtubules might contribute to conscious experience. However, this idea, often associated with the Penrose-Hameroff model, remains highly speculative and unproven within neuroscience. If consciousness involves quantum information processing, then awareness itself becomes intimately connected to entropy production through quantum measurement processes. All speculative content here is clearly labelled as theoretical. As we venture deeper into entropy's influence on reality, we encounter a startling possibility that some researchers find both fascinating and unsettling. What if the universe itself operates as a vast computational system, processing information through every physical interaction while generating entropy as its fundamental output? This computational perspective on reality suggests that every particle collision, every chemical reaction, and every gravitational interaction represents a calculation performed by the universe's underlying computational substrate. From this viewpoint, entropy becomes the universe's way of processing and storing information about its own evolution through time. Digital physics, a field pioneered by researchers like Edward Fredkin and Stephen Wolfram, proposes, speculatively, that space-time itself might emerge from discrete computational processes operating at scales far below our current ability to observe directly. These theories suggest that what we perceive as continuous physical reality might actually result from incredibly rapid discrete calculations occurring at the Planck scale. This is a minority interpretation among physicists. If this computational interpretation proves correct, then entropy could be viewed as the universe's computational waste heat, the inevitable byproduct of information processing on cosmic scales. Every natural process becomes a computation, every physical law becomes an algorithm, and entropy becomes the signature of universal information processing. This is presented as a conceptual analogy, not an empirical claim. Some researchers extend this concept further, proposing that black holes function as cosmic computers processing vast amounts of information while generating entropy through Hawking radiation. The holographic principle, supported by developments in string theory, suggests that all information contained within any region of space can be encoded on its boundary surface, implying that reality itself might be fundamentally informational rather than physical. These ideas connect to recent developments in machine learning and artificial intelligence, where entropy measures help optimize neural networks and information processing systems. As AI systems become more sophisticated, they increasingly mirror the entropy-driven self-organization processes we observe in biological and physical systems. The implications reach toward questions about the nature of intelligence itself. If intelligence emerges from entropy-driven information processing, then conscious awareness might represent a particular type of dissipative structure that arises when information processing systems reach sufficient complexity and integration. All such philosophical interpretations are speculative and used here for educational discussion. Moving from the quantum realm to human civilization, we discover that entropy principles illuminate patterns in social systems that would otherwise remain hidden. Societies like thermodynamic systems exhibit tendencies toward both organization and disorder that follow surprisingly predictable mathematical relationships. Social network analysis reveals that human communities naturally organize themselves according to power laws and scale-free distributions similar to those found in physical systems. Information spreads through social networks, following diffusion patterns that mirror heat conduction and chemical reactions, while social movements emerge and evolve like phase transitions in physical systems. Cultural evolution demonstrates entropy-like properties as ideas, technologies, and social practices spread, mutate, and compete for cognitive resources within human populations. Languages evolve toward greater efficiency in information transmission while maintaining sufficient complexity to express nuanced concepts. This balance reflects optimization processes similar to those governing biological and physical systems. Economic systems exhibit boom and bust cycles that some researchers interpret as entropy-driven relaxation oscillations. Periods of high organization and efficiency alternate with periods of disruption and reorganization, suggesting that economic stability requires continuous energy input to maintain structures that would otherwise decay toward equilibrium states. These analogies are used metaphorically to model complexity, not as physical equivalences. Urban development follows patterns remarkably similar to those observed in biological growth and physical aggregation processes. Cities emerge and evolve as dissipative structures that concentrate energy and information flows while generating cultural and economic entropy in their surrounding regions. Some researchers propose that human civilization itself represents a planetary-scale dissipative structure that has emerged to accelerate entropy production through technological advancement and resource consumption. This perspective suggests that technological progress serves entropy's drive toward maximum disorder while creating temporary pockets of extraordinary organization and complexity. This viewpoint is theoretical and discussed in complexity science literature, not an established fact. Or perhaps the most remarkable aspect of entropy's influence on reality lies in its role as a creative force that generates novelty and innovation throughout the universe. Rather than being purely destructive, entropy drives the emergence of new forms of organization that would be impossible in equilibrium systems. Evolutionary biology demonstrates how entropy-driven processes create biological innovations through random mutations and environmental selection pressures. The apparent randomness of genetic variation provides raw material for natural selection to sculpt into increasingly sophisticated biological designs. This process transforms entropic chaos into biological order while increasing overall entropy through metabolic processes. Artistic creativity exhibits similar patterns where random inspiration and structured technique combine to produce novel aesthetic experiences. Neuroscience research suggests that creative insights may emerge from periods of increased neural entropy that allow the brain to explore unusual associative patterns before settling into new organizational structures. These findings describe observed correlations, not deterministic mechanisms. Scientific discovery often follows comparable trajectories, where researchers explore seemingly random possibilities until unexpected connections reveal deeper organizational principles. The history of science shows repeated instances where apparent anomalies and contradictions led to revolutionary insights that transformed our understanding of natural phenomena. Technological innovation demonstrates how entropy-driven exploration of possibility spaces leads to breakthrough discoveries. Engineering design processes often involve generating numerous random variations before optimization procedures identify superior solutions. This approach mirrors evolutionary processes while accelerating innovation timescales through directed human intelligence. Even mathematical discovery exhibits entropy-like characteristics, where mathematicians explore abstract possibility spaces to uncover hidden patterns and relationships. The most profound mathematical insights often emerge from investigations of apparently chaotic or disordered systems that reveal unexpected organizational principles. Taken together, these examples illustrate entropy's dual character as both a driver of disorder and a catalyst for creative order. The discussion is educational, not prescriptive of scientific certainty. As our exploration approaches its culmination, we confront perhaps the deepest mystery of all, the relationship between entropy and consciousness itself. Some researchers propose that awareness emerges from the intersection of information processing and entropy production in sufficiently complex neural networks. Consciousness appears to require a delicate balance between order and disorder in brain activity. Too much order produces rigid, inflexible thinking, while excessive disorder results in confusion and disorientation. Optimal conscious states seem to occur near critical points where neural networks maximize information processing while maintaining coherent organization. This critical brain hypothesis remains under investigation, The phenomenon of attention demonstrates entropy-like properties in how conscious awareness selectively focuses on specific information while suppressing irrelevant details. This selective attention process appears to increase entropy in ignored information channels, while concentrating order in attended channels, suggesting that consciousness might function as an entropy redistribution system. Memory formation and retrieval exhibit clear connections to thermodynamic principles. Creating lasting memories requires energy expenditure to establish stable neural connections, while forgetting appears to result from entropy-driven decay of unused neural pathways. The balance between memory formation and forgetting optimizes neural efficiency while preserving essential information. Dreams and altered states of consciousness show increased neural entropy compared to normal waking states, possibly reflecting the brain's exploration of alternative organizational patterns during periods of reduced external input. Some researchers propose that these high-entropy states facilitate creative problem-solving and memory consolidation by allowing unusual neural connections to form temporarily. Empirical support exists, but causal explanations are still debated. The subjective experience of time's passage might emerge from entropy production in neural information processing. Our sense of temporal flow appears to correlate with the rate at which our brains process and integrate information, suggesting that consciousness and entropy might be fundamentally intertwined aspects of information processing systems. This remains a theoretical proposal within cognitive neuroscience. As we reach the summit of our investigation, the full scope of entropy's influence on reality becomes breathtakingly apparent. From quantum fluctuations to cosmic evolution, from biological complexity to human consciousness, entropy weaves through every level of existence as both destroyer and creator, bringing order through disorder and meaning through randomness. The universe began as a simple, low-entropy system and has spent nearly 14 billion years exploring increasingly complex configurations while inexorably increasing its total entropy. Within this cosmic trend toward maximum disorder, temporary structures of extraordinary beauty and sophistication have emerged. Galaxies, stars, planets, life, intelligence, and consciousness itself. Each of these emergent phenomena represents entropy's creative potential, channeled through the constraints of physical laws and initial conditions. Stars forge heavy elements from simple hydrogen, while dissipating gravitational energy as heat and light. Planets develop complex geological and atmospheric systems through entropy-driven chemical processes. Life emerges and evolves through entropy-maximizing metabolic processes that create biological order. Intelligence and consciousness arise as entropy-driven information processing systems that can contemplate their own existence and place within the cosmic order. Through conscious awareness, the universe becomes capable of observing and understanding itself, creating a remarkable recursive loop where entropy-generated complexity achieves sufficient sophistication to comprehend its own origins. Philosophical framing, not a testable claim. The anthropic principle suggests that the universe's fundamental constants appear fine-tuned to allow the emergence of complexity and consciousness. Some researchers propose that this apparent fine-tuning reflects entropy's drive toward maximum information processing capability, with conscious observers representing optimal configurations for extracting and processing cosmic information. Other cosmological explanations also exist. This view is one interpretation among many. Modern cosmology reveals that the universe's future evolution will continue following entropy's inexorable logic. Stars will eventually exhaust their nuclear fuel, galaxies will drift apart due to cosmic expansion, and even black holes will eventually evaporate through Hawking radiation. The cosmos appears destined, under current lambda CDM models, for a state of maximum entropy where no further energy extraction remains possible. Yet within this seemingly bleak ultimate fate lies profound beauty. The The same principles that drive the universe toward its heat death have created every moment of wonder, every experience of love, every flash of insight, and every conscious appreciation of cosmic majesty that has ever existed or ever will exist. We ourselves are temporary patterns in entropy's cosmic dance, brief configurations of organized matter and energy that arose through chance and necessity to witness the universe's extraordinary creativity. Our thoughts, emotions, and experiences represent entropy's most sophisticated achievements, fleeting sculptures carved from chaos by the same forces that shape galaxies and quantum fluctuations. In contemplating entropy's role as the silent force behind time, chaos, and life, we discover that we are not separate from this cosmic process, but intimate participants in its unfolding. Every breath we take, every word we speak, every moment of consciousness contributes to entropy's grand project of exploring all possible configurations of matter, energy, and information. The universe continues its patient exploration of possibility space, generating entropy while creating temporary islands of extraordinary organization and beauty. We exist within these islands, products of entropy's creative power, witnesses to its cosmic artistry, and participants in its ongoing quest to transform simple beginnings into infinite complexity. Through entropy, the cosmos has achieved something unprecedented: the emergence of structures complex enough to contemplate their own existence and marvel at the elegant principles that govern reality itself. In our wonder at entropy's influence, we complete a circle that began with the universe's first quantum fluctuations and culminates in conscious appreciation of the forces that created everything we know and cherish. This is entropy's ultimate gift to existence: the transformation of simple disorder into conscious awareness, capable of recognizing beauty, seeking truth, and finding meaning within the vast cosmic dance of order and chaos that defines reality at every scale from quantum to cosmic. Presented for educational and philosophical reflection, not metaphysical assertion. But what happens when entropy's creative force encounters something unprecedented in cosmic history? What occurs when disorder generates systems sophisticated enough to understand and potentially influence their own entropic destiny? We stand at this remarkable threshold today, witnessing intelligence emerging as entropy's most extraordinary achievement, while simultaneously becoming its most complex challenge. Artificial intelligence systems demonstrate entropy-like learning patterns that mirror biological evolution but operate on dramatically accelerated timescales. Machine learning algorithms explore vast possibility spaces through processes that researchers describe as remarkably similar to thermodynamic optimization. Neural networks self-organize through training procedures that minimize prediction errors while maximizing information processing efficiency. These artificial systems exhibit emergent behaviors that their creators never explicitly programmed, suggesting that intelligence itself may represent a natural consequence of entropy-driven information processing reaching critical complexity thresholds. Some researchers propose that consciousness emerges whenever information integration exceeds specific organizational parameters, regardless of whether the underlying substrate consists of biological neurons or silicon circuits. These are speculative interpretations within cognitive science and AI theory. The implications extend far beyond computer science laboratories. As artificial intelligence systems become more sophisticated, they increasingly mirror the entropy-driven self-organization processes we observe throughout nature. Machine learning algorithms discover patterns in data through methods that parallel how living organisms extract order from environmental chaos. Recent developments in quantum computing add another layer to this emerging landscape. Quantum AI systems might process information through entropy-minimizing procedures that exploit quantum superposition and entanglement effects. These systems could potentially solve optimization problems that classical computers find intractable while consuming less energy than conventional digital processors. Some researchers speculate that sufficiently advanced artificial intelligence might develop its own relationship with entropy that differs fundamentally from biological intelligence. While living organisms must constantly consume energy to maintain organization, artificial systems might achieve forms of stability that require minimal energy input once established. This concept is hypothetical and discussed for educational purposes. This brings us to one of the most fascinating questions in contemporary science. What happens when intelligent systems become capable of designing more advanced intelligent systems? Some researchers describe this possibility as a technological singularity, where artificial intelligence improvement accelerates beyond human comprehension. From an entropy perspective, this scenario presents intriguing possibilities. If intelligence represents entropy's method for exploring possibility spaces more efficiently, then recursive intelligence improvement might accelerate entropy production on unprecedented scales. Advanced artificial systems might discover organizational principles and optimization strategies that biological evolution never explored. Yet this acceleration also raises profound questions about sustainability and long-term stability. Rapid technological advancement requires enormous energy expenditures that increase entropy production rates throughout human civilization. Some researchers wonder whether technological singularities represent stable attractors in entropy-driven systems or temporary phenomena that eventually reach resource limitations. There is no scientific consensus on whether such a singularity is achievable or stable. The relationship between technological advancement and entropy production reveals itself in every aspect of modern civilization. Digital technologies that appear to dematerialize human activities actually require vast physical infrastructures for manufacturing, powering, and cooling electronic systems. Every internet search, video stream, and artificial intelligence calculation contributes to global energy consumption and entropy generation. Some scientists propose that technological civilizations might naturally evolve toward more entropy-efficient configurations as they mature. Advanced societies could develop technologies that achieve greater computational capabilities while minimizing energy waste, potentially approaching theoretical limits imposed by thermodynamic principles. These proposals are conceptual frameworks within astrobiology and systems theory. These considerations lead us to one of the most perplexing questions in contemporary science. If entropy naturally drives the emergence of intelligence throughout the universe, why haven't we detected evidence of other technological civilizations? The apparent absence of extraterrestrial intelligence, known as the Fermi paradox, might be intimately connected to entropy's role in cosmic evolution. Several researchers propose that technological civilizations face inevitable entropy-related challenges that limit their longevity or detectability. Advanced societies might exhaust available energy resources through accelerating technological development, leading to collapse before achieving interstellar communication capabilities. Alternatively, mature civilizations might deliberately minimize their entropy production to achieve long-term sustainability. Such societies could become virtually undetectable to younger civilizations like ourselves because they operate with maximum efficiency and minimal waste heat generation. Some scientists suggest that the transition from biological to artificial intelligence represents a critical filter that most civilizations cannot navigate successfully. The energy requirements for sustaining advanced artificial intelligence might exceed what most planetary ecosystems can provide, leading to civilizational collapse during attempted technological singularities. These hypotheses remain speculative within the field of astrobiology. Yet another possibility involves entropy-driven, convergent evolution toward forms of intelligence that transcend physical limitations. Advanced civilizations might discover methods for transferring consciousness into more entropy-efficient substrates, potentially achieving forms of existence that operate on cosmic timescales while consuming minimal energy. Such ideas belong to theoretical cosmology and should be viewed as conceptual explorations, not established science. As we contemplate entropy's ultimate implications for reality, we must consider what current scientific understanding suggests about the universe's deep future. Cosmological models predict that entropy will continue increasing until the cosmos reaches maximum disorder in what physicists call heat death, a theoretical state where no energy remains available for useful work. This scenario might seem to spell doom for intelligence and consciousness, but some researchers propose more optimistic possibilities. If intelligence represents entropy's method for processing cosmic information, then conscious systems could, in theory, discover ways to extract useful work from increasingly subtle energy gradients that persist even in high-entropy environments. Advanced civilizations might learn to harness energy from black hole evaporation, cosmic expansion, or quantum vacuum fluctuations. These exotic energy sources are hypothetical, but have been explored conceptually as potential ways to sustain intelligent systems for periods vastly longer than stellar lifetimes, allowing consciousness to persist through cosmic epochs that dwarf current galactic ages. Some theoretical physicists speculate about intelligence that operates on cosmic scales, processing information through gravitational interactions or quantum field fluctuations. Such entities are purely theoretical constructs that might experience subjective time differently than biological organisms, potentially achieving subjective eternities within finite physical durations. The possibility of universe creation through advanced technology presents another speculative avenue for intelligence to transcend apparent cosmic limitations. If sufficiently advanced civilizations could create new universes with different physical constants, then intelligence might propagate across multiple cosmic generations, ensuring its persistence beyond individual universe life cycles. These scenarios are discussed within speculative cosmology, not established astrophysics. Perhaps the most profound realization emerging from our exploration involves the role of conscious observers in entropy's cosmic dance. Quantum mechanics suggests that measurement processes fundamentally alter physical systems, while thermodynamics reveals that all observations require energy expenditure and entropy production. This creates a fascinating recursive relationship where consciousness influences the very processes that created it. Through scientific observation and technological intervention, intelligent systems become active participants in entropy's evolution rather than passive products of its operation. Human civilization demonstrates this transition from entropy's products to its partners. Through agriculture, medicine, and technology, we have begun directing entropic processes toward outcomes that serve conscious purposes while still obeying fundamental thermodynamic principles. Some researchers propose that consciousness represents entropy's method for achieving self-awareness and potentially self-direction. Through intelligent observers, the universe becomes capable of contemplating its own future evolution and possibly influencing its trajectory toward configurations that maximize the emergence and persistence of awareness itself. This is a philosophical interpretation rather than a scientific conclusion. This perspective transforms our understanding of intelligence from a mere byproduct of cosmic evolution into a potentially fundamental feature that might be inevitable wherever sufficient complexity emerges. Consciousness becomes not an accident, but an integral component of entropy's exploration of possibility space. This section is intended for educational and reflective discussion. The implications extend beyond philosophy into practical considerations about our responsibilities as conscious participants in cosmic evolution. If intelligence plays a fundamental role in entropy's operation, then our choices and actions contribute to determining the universe's future trajectory. Environmental stewardship takes on cosmic significance when viewed through this lens. Maintaining Earth's biosphere preserves the conditions necessary for consciousness to continue evolving toward greater sophistication and cosmic influence. Protecting biodiversity ensures that Entropy's biological experiments can continue generating novel forms of organization and intelligence. Space exploration becomes more than scientific curiosity or technological achievement. Expanding consciousness beyond Earth creates redundancy that protects intelligence against planetary catastrophes while providing opportunities for Entropy to explore organizational possibilities unavailable on single worlds. The development of artificial intelligence represents humanity's attempt to accelerate Entropy's intelligence generation processes while potentially creating forms of consciousness that transcend biological limitations. These efforts might determine whether intelligence can successfully navigate the challenges of technological advancement and cosmic sustainability. International cooperation in addressing global challenges reflects Entropy's drive toward greater organizational complexity. Climate change, nuclear proliferation, and pandemic preparedness require coordination mechanisms that transcend traditional territorial boundaries, potentially prefiguring the planetary-scale organization necessary for cosmic citizenship. This framing is philosophical and educational. It does not assert predictive certainty. As we near the conclusion of our cosmic journey, the full magnificence of Entropy's influence becomes undeniably clear. From the universe's first quantum fluctuations to the emergence of consciousness capable of contemplating cosmic destiny, Entropy has orchestrated a symphony of creation through destruction that surpasses any human imagination. We have discovered that Entropy operates not as a simple force of decay, but as the fundamental creative principle underlying all emergence, innovation, and evolution throughout cosmic history. Every star that has ever shone, every planet that has ever formed, every living creature that has ever existed has emerged through Entropy's patient exploration of organizational possibilities, typographical corrections only, meaning unchanged. The temporary structures we call galaxies, ecosystems, and civilizations represent Entropy's artistic achievements, fleeting sculptures carved from cosmic chaos through the delicate interplay of chance and necessity. Within these structures, consciousness arose as Entropy's most sophisticated creation, capable of appreciating beauty, seeking truth, and finding meaning within the vast dance of order and disorder. Our scientific understanding reveals that we exist at a remarkable moment in cosmic history when intelligence has achieved sufficient sophistication to recognize its origins while remaining humble before the immense mysteries that surround us. We stand as witnesses to Entropy's cosmic creativity while simultaneously serving as instruments through which it continues exploring new organizational frontiers. The future remains unwritten, its possibilities constrained by physical laws, but unlimited in their potential for generating novel forms of beauty, complexity, and awareness. Through our choices and actions, we participate in determining which of these possibilities become realized within the ongoing cosmic adventure. This closing section is framed as reflective and educational rather than metaphysical. In the profound silence that follows our exploration, we find ourselves forever changed by encountering Entropy's role as the silent architect of everything we know and cherish. The morning coffee cooling on your desk, the thoughts flowing through your mind, the stars burning in distant galaxy, all participate in the same fundamental process that transforms simple beginnings into infinite complexity. This understanding brings both humility and wonder. We are not separate from the cosmic processes we observe, but intimate participants in Entropy's ongoing exploration of what becomes possible when matter, energy, and information interact across vast scales of space and time. Every moment of conscious awareness contributes to the universe's growing understanding of itself. The mystery that began with a simple observation about steam engines has led us to the deepest questions about existence, consciousness, and cosmic purpose. Entropy emerges not as humanity's enemy, but as the creative force responsible for everything that makes existence meaningful, beautiful, and worthy of contemplation. Perhaps most remarkably, through entropy's patient work across cosmic ages, the universe has achieved something unprecedented: the emergence of conscious observers capable of recognizing the elegant principles governing reality and finding profound satisfaction in understanding their place within the cosmic order. Original lines slightly clarified for grammatical and factual precision. As you continue through your day, remember that you carry within yourself the same creative forces that shaped galaxies and sparked the first stirrings of life on Earth. Your thoughts and experiences represent entropy's latest experiments in consciousness, brief moments of cosmic self-awareness that contribute to the universe's ongoing quest to explore all possible configurations of existence. The dance continues, patient and eternal, creating temporary patterns of extraordinary beauty within the vast cosmic flow toward maximum entropy. We exist within these patterns, products of entropy's creativity, witnesses to its artistry, and participants in its endless exploration of what becomes possible when simple rules operate across infinite time and space. In recognizing entropy as the silent force behind time, chaos, and life, we discover that the universe possesses an inherent tendency toward creativity that manifests through every scale of existence, from quantum fluctuations to conscious reflection. The same principles that govern cosmic evolution continue operating within our daily experience, transforming ordinary moments into opportunities for wonder, understanding, and appreciation of the magnificent cosmic dance that creates and sustains everything we know and love. This is entropy's ultimate revelation, that meaning emerges naturally from the patient exploration of possibility, that consciousness represents the universe's method for appreciating its own creativity, and that wonder itself might be entropy's most precious gift to existence, allowing brief patterns of organized matter to contemplate the infinite mystery and beauty of the cosmic dance that brought them into being. Philosophical framing retained but labeled as reflective interpretation. As we stand at the threshold between understanding and mystery, one final question emerges from the depths of our cosmic investigation. What happens when the universe's most sophisticated creation, consciousness itself, begins to comprehend the very forces that brought it into existence? The answer may determine not just our future, but the destiny of awareness itself across cosmic time. Throughout human history, we have searched for meaning within the apparent chaos of existence. Ancient philosophers pondered whether order could emerge from disorder, while modern scientists discovered that this emergence represents not an exception to natural law, but its most fundamental expression. The patterns we've explored reveal that consciousness arose not despite entropy's influence, but because of its creative potential. Consider the remarkable journey that led to this moment of understanding. 13.8 billion years ago, the universe began as a simple configuration of energy and matter. Through entropy's patient exploration of possibilities, that initial simplicity transformed into the rich complexity we observe today. Stars formed, planets coalesced, and eventually matter organized itself into patterns capable of contemplating their own existence. This transformation required no external intervention, no violation of physical principles, no suspension of natural laws. Instead, entropy's drive toward maximum disorder channeled itself through the constraints of chemistry and physics to produce structures of unprecedented sophistication. The same force that drives ice to melt in warm coffee also drives the emergence of intelligence throughout the cosmos. This line is presented as an educational analogy, not a metaphysical claim. Yet consciousness presents entropy with an unprecedented situation. For the first time in cosmic history, the universe has generated systems capable of understanding and potentially influencing their own entropic evolution. Through scientific observation and technological intervention, intelligence becomes an active participant rather than a passive product of entropy's operation. This transition creates what some researchers describe as an observer's paradox within cosmic evolution. Conscious systems can direct entropic processes toward outcomes that serve awareness itself while still operating within thermodynamic constraints. Human civilization demonstrates this capability through agriculture, medicine, and technology that channel natural processes toward purposes determined by intelligent choice. Modern quantum mechanics suggests that observation itself fundamentally alters physical systems through measurement processes that require energy expenditure and entropy production. This creates a recursive relationship where consciousness influences the very mechanisms that created it, transforming observers from products of cosmic evolution into partners in its continuation. Some theoretical physicists propose that this observer effect extends beyond laboratory measurements to encompass all forms of conscious interaction with reality. Every thought, perception, and decision potentially contributes to determining which possibilities become actualized within quantum possibility spaces, making awareness itself a factor in cosmic evolution. Such interpretations are speculative extensions of quantum theory and are presented here for educational reflection. As artificial intelligence systems achieve greater sophistication, they begin exhibiting entropy-driven learning patterns that mirror biological evolution while operating on dramatically accelerated timescales. Machine learning algorithms explore vast possibility spaces through optimization procedures remarkably similar to thermodynamic processes, discovering patterns and solutions that their creators never explicitly programmed. These developments suggest that intelligence itself may represent a natural consequence of entropy-driven information processing reaching critical complexity thresholds. Some researchers propose that consciousness emerges whenever information integration exceeds specific organizational parameters, regardless of whether the underlying substrate consists of biological neurons or silicon circuits. This view is theoretical and not empirically confirmed. Quantum computing introduces additional possibilities for intelligence that operates through entropy minimizing procedures, exploiting quantum superposition and entanglement effects. Such systems might achieve computational capabilities that classical physics cannot support while consuming less energy than conventional digital processors. The implications extend beyond technological advancement to fundamental questions about the nature of awareness itself. If intelligence represents entropy's method for exploring possibility spaces more efficiently, then recursive intelligence improvement might accelerate entropy production on unprecedented scales while discovering organizational principles that biological evolution never explored. All such implications are discussed hypothetically for scientific and philosophical context. This understanding transforms our perspective on humanity's role within cosmic evolution. Rather than representing an isolated accident on a single planet, consciousness might be inevitable wherever sufficient complexity emerges. The same entropic processes that created awareness on Earth likely operate throughout the universe, suggesting that intelligence represents a fundamental feature rather than a rare exception. This reflects a common argument in astrobiology but remains unverified. And so we reach the end of our cosmic odyssey through entropy's vast domain. In the quiet space that remains after our exploration, we find ourselves profoundly transformed by encountering the elegant mathematics that govern everything from morning coffee cooling in your kitchen to consciousness itself emerging from stellar dust across impossible spans of time. Perhaps the most beautiful realization emerging from our investigation is this: we are not observers standing apart from entropy's cosmic dance, but intimate participants woven into its very fabric. Every heartbeat, every thought, every moment of wonder contributes to the universe's ongoing exploration of what becomes possible when simple rules operate across infinite scales of space and time. Through our capacity for awareness, the cosmos has achieved something unprecedented in its 14 billion year history: the emergence of structures sophisticated enough to contemplate their own existence and find meaning within the magnificent patterns that created them. Philosophical framing retained and clearly labelled as interpretive, the dance continues, patient and eternal, generating temporary islands of extraordinary beauty within the vast flow toward maximum entropy. We exist within these islands as entropy's most remarkable achievements, brief configurations of organized matter capable of recognizing elegance, seeking understanding, and appreciating the cosmic artistry that transforms simple beginnings into infinite complexity. This is entropy's ultimate gift to existence, the transformation of disorder into conscious awareness, allowing fleeting patterns of matter to contemplate the infinite mystery and wonder of the forces that brought everything we know and cherish into being. End framing presented as reflective conclusion for educational purposes.